Hi everyone, so here we're going to talk about how the atom was discovered and all the scientists that played a role in it. So you'll need your notes as well as the table of atomic theory. This will be at least a good table for you to jot down some extra notes, help you organize all the information. It's a good tool for you to help you remember all that info. So we're going to talk about atomic theory and then go through some practice questions. So first, there's this timeline that's in the Regents level textbook, so do take a look at that. That gives you a little bit more detail on each of the different levels, or different scientists that we're talking about here. So it all began in 500 BC, way long time ago. So Democritus was a Greek philosopher who said that all matter was made of atomos, which we later derived atoms from. Fast forward to 1803, we have the solid sphere model, and this was from John Dalton. If you take a look on the right-hand side, you see that the atom itself looked like a solid sphere. Dalton's atomic theory stated that atoms were made of solid, indivisible spheres, meaning that you couldn't break apart an atom. It wasn't made up of anything else except for just the sphere. All atoms of a given element are identical to one another in its mass and property, so one atom of oxygen is identical to another atom of oxygen. Compounds are formed from two or more atoms combining together. A chemical reaction is just rearranging these atoms, and molecules are made of atoms in certain proportions to one another. Most of these still hold true, and we'll kind of go through this not only in this lesson, but as we go through the school year. We'll find that this one and this one actually aren't true, but the rest of them, I mean, there's some truth in it, but the rest of them are, for what we know, as being accurate. The next comes in 1897, the plum pudding model by J.J. Thomson. So his experiment was a cathode ray tube. He pretty much just zapped atoms with electricity, and he saw that negative particles left the atom. So he concluded that atoms were made of negative particles embedded in a positive fluid. So if you take a look on the upper right-hand picture, imagine this as a cookie. All right, so the chocolate chips or raisins or whatnot, these are going to be your negative electrons. I'm going to write electrons as E dash, and then I do apostrophe to show the plural of it. And the rest of the cookie itself would be protons, or excuse me, positive charges. So we didn't quite know about protons yet, but we at least knew that there were some positive charges all around. So these little chocolate chips or raisins, those were all negative. Everything else was positive. Then in 1911, we have Rutherford's nuclear model. So we had he conducted something called the gold foil experiment. This is probably one of the most important experiments for you to know, so make sure that you do. So here we have a block where he actually pretty much bombarded a piece of gold foil with something called alpha particles. Alpha particles are positively charged. And so imagine that you had taken a sheet of tissue paper, really thin tissue paper, and you threw like a softball at it. You would expect that the softball would just go right through the tissue paper. And this is kind of what happened. So these alpha particles went straight through and hit the other side of the gold foil. However, some of them were deflected off to the side, and some even bounced back. So he was able to conclude that the atom was made of something else. So his experiment was to shoot tiny alpha particles, which are positively charged at gold foil. The first result was that the alpha particles went straight through, which is what we would expect, and that conclusion was that, or the conclusion was that the atom was made of mostly empty space. The second result was that some of the alpha particles bounced back or were deflected, and the conclusion based on this was that atoms had a dense positive core. Remember, alpha particles are positive, and so for them to bounce back off of something, that other thing should be positive as well. All right, so here's how we get the nuclear model, that there was something else inside of the atom, and there was a dense positive core. We'll keep going. Then we have the solar system model from Niels Bohr in 1913. So pretty much, and we see this in fireworks and neon lights, and we'll actually explore this a little bit more in the next section, but light is given off whenever elements are exposed to any heat or flame or electric fields. So he was able to conclude that electrons actually orbited around the nucleus. These negative particles were just surrounding it. And in certain levels, we can sometimes call them energy levels or shells, and that each of these energy levels, each of these electrons had different amounts of energy based upon how close they were to the nucleus itself. The proton model, well, this was Ernest Rutherford again in 1918. He was still able to conclude that the nucleus contained protons. He named those protons for the positive charged particles in there. Then in 1927 and 1932 we had the wave mechanical model. Several scientists were part of this, but two of the most notable were Heisenberg and Chadwick. So Heisenberg was able to conclude that the electrons were most probably found in orbitals. Chadwick said that the electrons moved as both particles and as waves. And he also concluded that there were also neutral particles in here called neutrons in there. Let me make sure I get that in there. So the nucleus itself is made of positive protons and neutral neutrons. Actually, that should be, there we go. Alright, and the reason that the nucleus has these neutral particles is that, say if we had 15 protons, all the protons are positively charged, and since they have the same charge, they would pretty much go away from one another. They'd be deflected from one another or repel one another. Those neutral neutrons were in there to help kind of offset some of those positive protons, so that way the protons and the neutrons could still be in the nucleus at the same time. Now, these were some of the scientists that helped discover the theory of the atom. So make sure that you do know that there's tons more scientists in there, but these are the most likely that you're going to be responsible for knowing. And yes, you are responsible for knowing them. Do know, let's see, you don't need to know the exact dates or the years. I just kind of threw that in there to kind of give you some nice little range. You do need to know what the little bullet points I have here there are. So like pretty much their experiments, the results, their conclusions. And it does help to know some of their names as well. Last names, don't worry about the first names. Alright, so here's some questions that you might see from the Regents, and these are all Regents-based questions actually. So in the wave mechanical model of the atom, orbitals are regions of the most probable locations of. Alright, so if we see, anytime you see orbital, I want you to make sure that you know that those are going to be electrons. The next question, which of the following phrases describes an atom? So let's go through this. So we have positively versus negatively charged electron clouds. So let's think about electrons. What charges are electrons? We know that they should be negatively charged. So let's go ahead and get rid of A and B. And now we're down to C and D. So let's keep reading the rest of the statement. So the positively charged nucleus or a negatively charged nucleus? Well, inside the nucleus we know that there are protons and neutrons. Protons are positive, neutrons are neutral. So overall, the nucleus itself should be positively charged. So you should have had C for this one. The next question. What was concluded about the structure of the atom as a result of the gold foil experiment? So again, you do need to know the experiments. So let's think back to the gold foil experiment and who did that. We know it was Rutherford's experiment. He took alpha particles and bombarded a piece of gold foil. Some of those particles went straight through. However, some were deflected and some even bounced back. So the result of this, result of the gold foil experiment, we know that since the particles did go through, that the atom was made of empty space, mostly empty space, because a whole bunch went through. However, since some of them deflected or bounced back, there had to be some sort of positive core. Right? So which one of these statements helps us figure that out? So let's see. A positively charged nucleus is surrounded by positively charged particles. You don't have that, because we know that overall it should be negative around. A negatively charged nucleus, we should pretty much kind of pause there. You know that the nucleus is positively charged, but it's surrounded by mostly empty space. So we know that since we had the negatively charged nucleus, that made this statement wrong. For C, a positively charged nucleus is surrounded by mostly empty space. That checks out. And let's just keep reading. D, a negatively charged nucleus. We know that's wrong because the nucleus is going to be positive. There we go. So C is our answer for that one. Which sequence represents a correct order of historic developments leading to the modern model of the atom? So we knew that the first model was going to be from Dalton. It was a solid sphere. Then J.J. Thomson had the plum pudding model, and then Rutherford, and so on and so forth. So we should know that it started out with a hard sphere. The most recent discovery was that electrons are in orbitals around the nucleus. So if we take a look here, we want the hard sphere to be the first part of this, so the atom is a hard sphere, good. B, most of the atom's empty space versus the atom is a hard sphere. This one went before. The atom is a hard sphere. Let's see, keep going. And then D, most of the atom is empty space. Electrons exist in orbitals around the nucleus. So far, these two are incorrect order. However, that should have been first. So let's keep going back. A, the atom is a hard sphere. Electrons exist in orbitals around the nucleus, and most of the atom is empty space. So the empty space part went there. So the atom is a hard sphere. Most of the atom is empty space. Electrons exist in orbitals around the nucleus. That should be your answer. Alright, electrons have properties of A, particles, B, neither particles nor waves, C, waves only, or D, particles and waves. So according to Chadwick in 1932, electrons have properties of both particles and as waves. So to summarize, there were a whole bunch of different scientists over a long period of time that helped us come to discover what the atom was actually made of. And I'm sure as we continue on, we'll find more discoveries as well. Have a great day, guys. Take care.